Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to try to evaluate the surface area generated by revolving the curve parametrized by the parameter t. So x equals t cubed over 3 and y equals t plus 1. And we're talking about the piece of that curve corresponding to t equals 1 and t equals 2. And we're going to revolve the curve about y-axis. So this is another classical problem of calculus that we tackled earlier when the curve is given in the rectangular equation form. In fact, we developed a formula for that. And I want to show you what formula we're going to use for finding the surface area when you have the curve in the parametric form. Let's say you have x equals f of t and y equals g of t provided to us. Let's say like we are talking about a smooth curve, so that means there's no break in the curve. Okay, and then we're given interval a and b for t, and you have two different formulas here. One is the revolution about x-axis, and the other one is the revolution about y-axis. So different from the arc length formula, that square, the radical part by itself was corresponding to the arc length, but you have the 2 pi times g. That's in fact the circumference of the frustum, and multiplying the uh, arc length of that, and that's going to give us the surface area of the frustum. Okay, so circumference times the arc length. Okay, so we're going to use this formula, and then let's see what kind of curve we should expect to start with. I think that's a parabola-looking curve. So essentially, we're going to revolve this around y-axis, and there's going to be a surface generated by that, and we'll be finding the surface area of the three-dimensional object. All right, let's get started. All right, so we're going to find the surface area generated by revolving the curve about the given axis, which is the y-axis in this case. So the curve is parameterized as like x equals t cubed over 3 and y equals t plus 1. And t's are stuck in between 1 and 2. And here is what it looks like. You can also graph this curve by yourself. Okay, so we're going to revolve this curve around y-axis. And let me just show you how it looks like when you have when you look at the 3D version of this. Okay, so there we go. All right, so this is our curve. Here's our y-axis. The revolution is going on in this direction. Okay, so here we go. So if you just keep revolving that around, this is exactly the shape you want, and you want to find the surface area of this three-dimensional object. Okay, so essentially you want to find the surface area right here. Okay, and let's see what formulas do we have. So we have the area of the surface of revolution in parametric form. As I said, we have two different versions of that. One is revolution about the x-axis. The other one is the revolution about y-axis. So we are, in fact, in this case here. Okay. And this f of t is in fact what we have x of t here. So you're going to have 2 pi times x of t, and radical you have x prime squared or dx over dt squared plus dy over dt squared. Okay, so I'm going to try to use this formula in the next slide, and let's see what we're going to get. All right, so we have we need dx over dt and dy over dt. All right, let's just plug them back in as well. So I already plugged in t cubed over 3, plus we should put the limits of the integration. This is going to be from 1 to 2, 1 to 2, t cubed over 3. So dx over dt is 3t squared over 3. So that is t squared. So I take the square of that. Plus dy over dt is 1. 1 squared is just 1. Okay. So in turn, what do we have? 2 pi. And I go from 1 to 2. In fact, I can pull out 3. So I can make it 2 pi over 3. So I have t cubed, t to the 4th plus 1, and dt. Okay. So this is a nice U substitution problem. So I'm going to have a little space in my next slide and try to integrate this definite integral. All right, here we go. So I have rewritten the indefinite integral version of that. And this is a good U substitution problem. And you should probably call inside the radical to be U. So that du equals 4t cubed dt. So here we go. I'm going to replace this integral by the u version of that, which is 1/4 du. And in fact, you have also a radical u here. Okay? Because t cubed dt is 1/4 du. And this is equal to 1/4 u to the power of 1/2 du. Okay? And 1/4 u to the 3/2 divided by 3/2 plus c. Okay? Flip the bottom over, that's 2/3, and you have another 1/4 over there, so you have 2/3, you're 1/6, and then you have t to the 4th plus 1 to the power of 3/2 plus c. Okay. All right, so I'm going to use this towards my calculation of the definite integral here. So you have 1/6, 2 pi over 3. Let's just continue from here. 2 pi over 3, 1/6. Okay, t to the 4th plus 1 to the power of 3/2. Integral from, limits from 1 to 2. There's no integration anymore because we're done. Okay, so let's just clean this part up. Okay. There we go. So I'm going to continue from right here. Okay, so this is pi over 9, in fact. Pi over 9, t to the 4th plus 1 to the power of 3/2. 1 to 2. We're using the fundamental theorem of calculus now. Okay, so let's plug in 2. So you have 17 to the power of 3/2. And we are plugging in 1, so this is 2 to the power of 3/2. So this is the exact expression, but if you want to get an approximation for this and use your calculator, and you're going to get something like 23.48. Okay. So the surface area I mentioned earlier is 23.48 units. Okay. All right, this takes care of everything in this question, and I'm going to stop right here. Thanks for watching. I'll see you in another video. Bye.